Welcome everyone. Today we will be reviewing Unit 7, the waves.
Okay. Waves, what are they? Waves are vibratory disturbances that propagate through a medium or space. They transfer energy and not mass. That is very important to remember. So waves in a medium can include waves going through water, rope, slinky, and a spring, and air. Waves in space are usually electromagnetic waves. They include microwaves, visible light, X-rays, etc., and they can be found on page 2 of the physics reference table. There are two types of forms of waves. So we have pulse and periodic waves. A pulse is a single vibratory disturbance, while periodic waves are repeated disturbances, and both of them can take on any shape. Within periodic waves, there are two different types. So we have longitudinal waves and transverse waves. They are basically the same thing, but the main difference is that longitudinal waves are where particles of the medium move in a direction parallel to the direction in which the wave moves, and transverse waves, they move perpendicular to them. So, all right. So here we can see this is a transverse wave and this is a longitudinal wave. In longitudinal waves, you can see this part. This part would be considered the compression, and the extended part here would be what would be called rarefactions. So in longitudinal waves, they must have a medium to travel through, while transverse waves, they don't need a medium. Wavelengths. Wavelengths, the definition of a wavelength is the length of one wave or the distance between corresponding points. It is represented by the symbol lambda, as you can see here, and it is measured in meters. Here we can see that the crests are the maximum of the wavelength, and the trough is basically the minimum of it. One wavelength is it can be from crest to crest, trough to trough, or a point from the principal axis to another point there. So in phase and out of phase. Any 2 points on a wave that are one or more whole wavelengths that are apart are in phase. Keyword here is whole wavelengths. So if it's only one wavelength, if it's only 1.5, it wouldn't be considered in phase. For example, this would be considered in phase. But if it were to extend just a little further, this would be considered out of phase because it's not one or two whole wavelengths. The amplitude is the maximum displacement from rest position from the principal axis to the crest or to the trough. So for example, A to B would be an amplitude, or from C to D, that would be measuring the amplitude as well. The amplitude measures the amount of energy. So for example, in sound waves, if you increase the amplitude there, then you raise the volume. And in light waves, if you increase the amplitude for light waves, it increases the brightness. Moving on. The frequency of waves is the number of wavelengths or cycles per unit time. So if there were 5 cycles in 1 second, that would just be 5 cycles per second. And it is measured in hertz. The period is the time it takes for one wavelength to pass, and it is measured in seconds. We can find that out from the formula. Period equals 1 over frequency, or frequency equals 1 over the period. To find the speed of the wave, which is the velocity, it can be found using the formula velocity equals distance over the period, or when we substitute it, it could be the wavelength divided by the period, which simplifies to the velocity equaling the frequency times the wavelength. So here we have an example problem. It says the diagram below represents a periodic wave traveling through a uniform medium. Here it is. If the frequency of the wave is 2 hertz, the speed of the wave is, so here in the diagram, we see that from this distance to this distance is 6 meters, but that is 1.5, 1.5 wavelengths. So to find for how much it is for one wavelength, we would have to do 6 meters divided by 1.5 wavelengths to find how much it is for one wavelength, which in this case would be 4 meters per wavelength. Then all we have to do is substitute it into the formula here, and here we get the answer should be 8 meters per second for the frequency. The last part would be wavefronts. So there are two different types that it could be shown in: point source and line source. So point source, if you can visualize it, it would be like throwing a pebble into the water. And the pebble, wherever it hits the water, that would be the epicenter. And it would have like a rippling effect. So here, the solid lines would be represented as crests, and the dotted lines would be trows. So for example, how to read this would be from, if you were to read it, it would be from dotted to dotted would be considered one wavelength because it's from trow to trow, or solid to solid would be crest to crest. If it were from dotted to solid, then it would only be half a wavelength.
So now we're going to talk about the Doppler effect. So the Doppler effect is an apparent change in frequency observed by a stationary observer as a point source, which Joey described in her part of the presentation, moves. So the Doppler effect can be seen both in sound waves and light waves. For sound waves, a good example of the effect is with an ambulance. As you can see in the diagram here, if an observer is standing to the right and an ambulance is passing them, then the frequency they observe is higher, and so they hear a higher pitch. On the other hand, if observer is standing on the left, then the pitch is lower because they're observing lower frequencies. As for the light waves, the same thing occurs, only you see increased frequency as blue shift and a lower frequency as red shift. So an observer standing on the left of this point source would see red light, or red shift, an observer standing on the right would see blue light, also known as blue shift. So the Doppler effect has several real-world applications. For example, it's used with radar guns that measure the speed of a car as it's passing by. It is also used in weather forecasting to track movements of precipitation, storms. And of course, it's used in cosmology to track movement of galaxies and stars, because galaxies that are moving away from us would display redshift, while galaxies that are moving towards us will display redshift. Now let's talk about wave interference. Wave interference happens when two waves meet while traveling on the same medium, and they can interact in several different ways. The principle of superposition just talks about constructing a new wave by adding two or more waves together. As you can see in the first example, if you have two waves that have this displacement in the same direction, you just add them to construct the same wave. In the second example, the two waves have displacement in opposite directions. So the new constructed wave would favor the side with a larger amplitude. So you can see the new wave would be a combination of both of them. So constructive interference is what can be seen in example number 1. And it is when interfering waves have the displacement in the same direction. For example, two crest pulses moving in opposite directions. As you can see here, when during the interference, their amplitudes would almost combine, and you would have one wave with a larger amplitude. The same happens with two throws moving in opposite directions. You can see that a new wave would be produced with the combination of the two pulses. And maximum constructive interference occurs with a phase difference of 0 degrees, which occurs when two crests meet or two throws meet. On the other hand, destructive interference occurs when two interfering waves have displacement in opposite direction. A good example of this is one crest and one throw of the same amplitude meeting while traveling in opposite directions. As you can see in this example, because the amplitudes are the same, the crest and the throw would basically cancel each other out. So the new wave would not have an amplitude. And in the second example, you have one crest and one throw of different amplitudes, but still displacement in different directions, moving in opposite directions. So here, because the throw has a greater amplitude, the new constructed wave during the interference would favor that side. And of course, maximum destructive interference happens with a phase difference of 180 degrees. So basically like a crest and a throw canceling each other out because they would be 180 degrees apart. And the last topic that we will cover is resonance. So objects naturally vibrate at their own frequencies. So resonance occurs when frequency of a wave matches the frequency of the vibration of an object. And this principle is very important in construction of bridges because you don't want them to collapse. And also, like, people can break glass with their voice by matching the frequency of their voice with the frequency of the glass. Question here, number 20, is asking about pulses. So you can see here you have two pulses of different amplitudes, but their displacement is in the same direction and they're moving towards each other. So the question is asking what the medium would look like after the pulses have passed each other. So they're actually not asking you to combine the pulses or anything like that. But you would do, so the pulses themselves would not be changed by their interference with each other. So the answer to this question would be B, because the right pulse would just carry on like it was before in the same direction with the same amplitude, and the left pulse would just carry on going to the right, and they would not be changed by their interaction with each other. So that's choice B. So I think that is a wrap for waves. I hope you have enjoyed this.
In.